Hi folks, welcome to The Breaking. My name's Henry, and today we're going to look at the new hotness of FujiNet for the TRS-80 color computer, which is a full bus version. Now, I must remind you that this is in the bodge and breadboard stage. It's very early on. It's very new as far as we haven't even figured out how to put everything together yet. And the code as stands seems to be working for the CoCo 3, however, stalls out on the CoCo 2. I have my thoughts because I've done a little bit of review of what's going on as to what might be part of the issue. However, there's stuff here that we need to learn, some basics that I don't even understand yet that I need to have figured out in order to be able to grok what's going on with the system as a whole. So just sit back, relax, and enjoy the ride as we go into the full bus FujiNet device for the TRS-80 color computer. This will be an adventure. So what do we have for this new FujiNet goodness? Well, first of all, we're upgrading the ESP32 device. So this is going from the old one to the S3. The second puzzle is Raspberry Pi Pico, or excuse me, Raspberry Pi Pico, or a P-ish device. S3 will be that interface itself, and this will serve as bus arbiter and also handle ROM emulation and a few other things that deal with like the CoCo side of things. And all that for right now, because this is still very much a work in progress, both hardware and software wise, is going to go on a proto board that doesn't have much on it. And it breaks out all of the signals from the CoCo port onto this header. This will use the so-called Becker, which is just basically a couple of addresses in I/O space that have been used in the emulation community to implement drive wire on emulators, and we're going to leverage that. I want to get these soldered up together. I want to see if I can't compile the firmware and then see about installing it. So we'll start at least with just the normal soldering month. How about that? That sounds like fun. L. Curtis Boyle, I'm looking at you. Have fun doing this if you just gave yourself a shot. All right, so quick aside, some of you may not understand how soldering actually works. So just a real quick aside on this one. The idea is that you want to get heat on both of the objects that you solder together. So in this case, I want heat on the pin and on the pad. And then you do that, and if you've got enough heat on there, then by touching it to the pin, that will actually melt not on the tip of the iron, but on the pin itself. Watch real careful and happen again, or on the pad, depending. You may hear about something called reflowing a connection or reflowing a solder joint. And literally all you're doing when you're reflowing the joint, maybe adding some flux to it. Give me a second. Let me flux. May add some flux to it to allow the solder to flow more freely. And the flux also helps with removing oxidation layers so that the solder can actually bond. But reflowing is literally iron onto a cold joint. Well, it might be a cold joint. That's a technical term also. But a soldering joint that is solid. And then heating it up, letting the solder melt, letting it flow. And the iron to allow. The technical idea of a cold solder joint is a solder joint where, yes, the solder melted, but the bonding points, say the pin and the pad, one or both of them were cold and the solder did not wet them. When we're done, what we want to look for is any evidence of soldering of the solder joint that did not flow appropriately, that did not wet appropriately, or that might be bridged. I'll set this off to the side. We'll move on to seeing if firmware will build. And now to try building and programming. I'm not sure what to expect. I've cloned the most recent repository that I'm aware of for development, and it will simply running the incantation, which I hope will work. Okay, so we already have a failure. Let's see what happened with that. I have no earthly clue what's happening here. So after consulting Discord, and specifically Moswald, looks like there are a few incantations that I'm going to have to do. And in this particular case, I'm okay with using these incantations simply because there's so much about the build system here that I don't really understand what's going on. That's all right. So when last we left our heroes, we had a bunch of silly error messages, and I'm told that if I remove a specific component that it will start working. It's in here, it's in components S3, and apparently this little thing right here, ESB modem USB DTE, doesn't need to be there. So after having done that, I should be able to do a successful build. Let's try it. And in the background, I hear the fan spinning up. And we're moving along. Okay, that's farther than we got before. That's promising. Excellent. It built. Now, what I thought was going to happen was that this would program the ESP32 to program the Pico. Apparently that's not the case yet. So I have to manually compile the Pico stuff, which shouldn't be that big of a deal. And we have Atari 2600 CoCo Max, so we're doing CoCo, obviously. And I have to do a CMake. So it's complaining about that. SDK location was not please set Pico SDK path or set Pico. We'll just do that. Fans are spinning up. All right. Oh, that was quick. Let me pull this out because that's not going to be necessary at the moment. I should be able to get these programmed. First trick is going to get the Pico programmed. Oh, no, not yet. I have to make it. That CMake doesn't actually build it. CMake sets up the build environment. So there we go. Okay, that built. And I do have a main.uf2. Nice. All right, so that's loaded in there. So it looks like things are working so far. And the next trick is to see whether it will boot a CoCo. Pop the hood. Nothing. Okay. Oh. This must be what Moz was talking about. I'm tapping on the keyboard here, as I'm sure you can hear, but nothing's showing up on screen. So that was where, I think that was where we left our heroes in the conversation that I was a part of on the Discord. So now it's time to dive into what's happening with the Pico, because the Pico is going to be what's holding that up, I do believe. Let me make sure that when I turn this off and remove the device, the keyboard is actually working. And, well, that wasn't good. Give it a second to actually clear its memory, maybe. There we go, that's better. Yep, everything's working fine. What do we have so far? We have built the device. We've discovered that there is a problem with keyboard entry once this is plugged in. Otherwise, without it plugged in, it works fine. And we've discovered that it does build, everything builds fine. We're just not sure what's going on over here. So the next step for me will be to experiment with the Pico code, and I don't think I need the ESP32 for that. I think I will try that now. Remove the ESP32, bring this up, and see what happens. Insert cartridge. That. And get back to the front screen. Did I get back in? I hate it when I do that. Should do the trick. Everything looks good. All right, so it's blocking. Ooh! That's very interesting. That's what I thought I saw. All right, check this out real quick. So that right over there, where the cursor is blinking, look at the rate that cursor is blinking. Yeah. 2, 1, 2, 1, 2. It's about like that kind of a tempo. So I'd have to have a tap to get that, but at least I know I've got the Met in my head now. Thank you, several years of marching band, for giving me a Met that just kind of sticks around in my head. Yes, that's definitely running much slower. Again, look over there and check that tempo out. Note to editor self, take a moment to cross-compare this one with the one before it. Because there's definitely a difference between the two. Actually, that might be something I looked at before. But that's a slowdown, and it's also sending in phantom keystrokes. I'm not even touching the keyboard. Okay, I think I know roughly what's happening, but I will need to dive into what the Pico itself is programmed to do to make this, to figure this out. So that, we'll see what happens with that. At the very least, I know that it's at the state, I know that it's working to the state where Moz had it in the past. Okay, cool. Let's see what happens next. Right, I think for the next test, I want to see whether this cartridge causes me problems without anything plugged into it. Let's see if it happens if I take the Pico out of its success. All right. And then put this back in and make sure that I don't have... Oh, really? Come on. All right, fine. Gotta pop the hood to see what I'm doing. That's back in place. Let's see what the CoCo does when I do that. Let's... Okay, this all looks right. So, with that, let's try to reprogram the Pico, or I'm sorry, not reprogram the Pico. Let's try to clear the Pico out. That was annoying. I didn't already have it in the SDK. All right, awesome. That should have cleared it. Get this installed again. The USB goes in that direction. There we go. Pop you into place. And let's check what's going on here. Okay, everything's fine. We know that the problem is not just simply the Pico being put in there. What is the... Let's get this out of the way. Where did I put that schematic? All right, let's take this over to a more appropriate location. And let's see what we've got going on. What is this connecting to on the CoCo bus? CTS and SCS. I know what those do. CTS is our cartridge select, and that gives us the C1000 to E1000 range. And SCS is the secondary select, which gives us the F1000, I believe. No, the FF400 to, or FF40 to FF50F range, I think it is. I'll have to look at the SAM part. I'll look at the schematic to make sure. But either way, those are there, and I want to see which ones it's actually listening to, which I will find out by looking kind of sort of over here. And we see CTS, we see the cartridge select. I do not see SCS being added to anything. That's data ground, data, address ground, address. That's the read-write pen. That's the... Okay, we've got the E, not the Q, and we probably need both the E and Q to be able to decode a few things. Let me see. We've got ground, cartridge select, non-maskable interrupt. And these are going over to the ESP32. Those are 3 volt and 3. And so, what do I need to actually take apart here? This is only going to be feeding C1000 and up. So there's some high bits that I don't need. I'm fairly sure. So I'm really not sure how far we're going to get in this particular video. I do know that I want to at least get a start on understanding what's happening with the Pico. It looks like the Pico is our bottleneck here as far as what's causing things to not go right. The FujiNet's firmware itself on the ESP32 is relatively mature, and all we have to do is put together the interface. I've got 2 interfaces that I've got to work with. That's the cartridge interface, and that is the interface addresses at FF40 through FF5F, in which lies the addresses that we're looking at transferring over for FujiNet use. So all that said, I need to do the following with the Pico and understand what's going on. I need to implement cartridge emulation. Implementing cartridge emulation should be simple. All I need is to decode C1000 through E1000, actually through D1000, FF, and whatever the heck. Let's see, decode that, respond to cartridge select, and provide cartridge data based on the address. And in cartridge emulation, this is a read-only operation. Then the other thing I need to do, that's spelled wrong, is implement the Becker port. This will respond to SCS. It is a read-write pair. One of the addresses is going to be, I believe one of the addresses is read and one of the addresses is write. And I'm going to take a moment to research that just to be sure, so expect fast forwarding. FF41 and FF42. All right, it just pulls the data bus in. Okay, it pulls D0 through Z7 and A0 through A7, pops that in there. Oh, you know what? I don't think we're capturing the read write. Are we capturing? We are. Okay. GP24 is capturing read write. We're capturing E, so we've got that. We need to know whether this is a read or this is a write. FF41 should only be a read. So we've got the data read and we've got the data write. All right, I start to see what's going on with this. So the Becker part lives at FF41 and FF42. FF41 is the status information, and in this case, bit 1 of FF41 is the only one we're looking at, and FF42 is the read-write port. So I need is a pair of ports. FF41 is read-only. So that's all we're looking at is bit 1, and we're getting 0 offset, so that is literally bit 1 is if that's set, we've got data available, otherwise we don't have data available. FF42 is read-write, and that's our data port. Can I do that in the PIO code? Can I listen to the read-write in the PIO code? Listen to the read-write, and I'll just map this out, and let's see how it works out. Listen to the read-write. Listen to read-write, and SCS, CTS. Okay. If it's SCS, then we are doing the Becker port on. It's a CTS. Let's see. So that's going to be the lower bits, and I only need, because of this, A0 through A12. Well, I'm already thinking about this in logic gate format, and the PIO's not going to do that. And PIOs don't do comparison like that. It feeds it or it doesn't. Only need A0 through A12 to decode everything I need. I need to make sure that all the attached GPIOs default to input, because if they default to, yes, I need them to default to input, because if they default to input, they will be high impedance on the bus. Listen to read-write, SCS, and CTS. Make sure I'm listening to those because they're going to tell me different information. Verify on the SCS. I want to verify that A0 through 7 is 41 or 42. Outside this range, we're doing nothing. Because those are the only 2 ports we're interested in. On 42 and write, set write on ports according to timing. And 42 and write is the only conditional thing. Anything other than, if it's 41 and write, we'll just silently not. We're not going to do anything there. CTS, prep cartridge address. And on this one, we want to send A0, 12 to the, let's see. And once we've got that, and this feed the data from the LUT. That's actually quite simple. Prep cartridge address. That's all I need to worry about there. So for the cart ROM, that's literally everything I need to do. There's very little in the way of processing. So really, the question then becomes, how do I sequence this in the Pico itself? Because it strikes me that at any time I could be getting an SCS or I could be getting a CTS. How much do I want to feed to the Pico, and what do I need the PIO to do as a result? So the PIO should only assert the data bus when there is an actual write, or when there's a let's see, it should set write ports according to timing. 41 and write, no, that's only read. Okay, so the PIO should assert the data bus only when the CoCo says, I'm reading things. I'm not writing things, I'm reading things. PIO SM get blocking SM address. So really, I want to grab the entire state of the bus into that. We get the RW pen, and I want to test that out. So I don't even need to worry. I can just use the FIFO for, the FIFO for that to manage all this. This adds a little bit of latency. Get RW pen, because I can grab CTS, I can grab SC or CS cartridge select, I can grab secondary select, I can grab read write, all those pens, and throw those onto the bus. The problem I'm facing here is I'm not quite good enough at this to separate out where PIO begins and where PIO ends, and the Pico itself, the RP2040 processor, the ARM core needs to begin. Where does PIO end and where does ARM begin? That's what I'm looking for. Where does ARM end and where does PIO begin? What do I need the PIO to process? What signals do I need it to set? And how am I going to affect that? If I can manage to get everything to work in a single word of memory and have everything be fine in that regard, then that will be nice. So after looking at what this code is trying to do, not only here but elsewhere, I've managed to do a little bit more grokking of how the PIO works, and I've managed to do a little bit more grokking of what we're trying to do. Here's where the beauty of this comes in. There's actually a limited scope of decoding that we need to do, because we've got the SCS line, and the SCS line comes over and hits select number 6 out as with a 0 basis. So that's going to be select equals 6. This may show as select equals 7 in the SAM literature. I'm not really sure. And then we've got the cartridge select line, and the cartridge select line is select 0, 1, 2, 3, select equal 3. So if I look at the SAM, we have S equals 6 as IO2 space, which is FDF 140 through FDF 150F. So that means that I can use SCS to know that I'm already in this space when the only two ports, especially since the only two ports I need are FDF41 and FDF42. With the cartridge lives in S equal 3, again, cartridge select, and that gives me C1000 through FDF100. Actually, FDE FDF, but FDF100 being the top of the next region. So if I wanted to decode the entirety of the space all the way up to FDE, FDF, I would have to have 14 bits for the address bus. However, since we are looking at what the CoCo 2 can do, and the CoCo 1 can do as well, and since historically we've been looking at 8K cartridges for that, we're only needing to decode between C1000 and DFFF, which means I only need 13 bits. So now I have 3 extra bits that I was using in the old area. You can see right here that we had data 0 through data 7 and address 0 all the way up and through address 15. So I only need A0 through A12, and then A13, A14, and 15 can be free if I decode both CTS and SCS. CTS is already there. I do need the read-write line. The read-write line is already here, right here on sitting on pin 27. And I should also have, the CTS line is already there. I've got non-maskable interrupt available, which is not currently being used, it looks like. I'll have to double check the code to make sure that NMI is or is not being used. It might be. So I want to leave that be. We do have, let's see, what other lines get hooked up? Address, read, write, E, ground, CTS, NMI. Looking at the timing diagram of, oh, I need to move this out of the way. Looking at the timing diagram of the 6809, the address bus will be there by the time Q goes high. But we don't need to decode that because according to the timing diagram, there we go. In slow mode for the SAM, the address bus will go into a valid state before the selections are put into a valid state, and then you've got the decode logic from the demultiplexer, so you're going to have a little bit of time. So once SCS and CTS are asserted, once either of those are asserted, we know that we have a valid address on the bus, so I don't have to worry about the rising edge of Q. So with the valid address on the bus, I so far don't need Q. The only thing left is when is the data valid? And we know that if the 6809 is writing, that the data will be valid somewhere around the rising edge of E, but we also know that the data is guaranteed to be valid by the falling edge of Q. By the same token, since we know that the 6809 will be asserting the data bus somewhere during this time around the falling edge of Q, then we are safe to assert the data bus on the falling edge of Q and have the plenty of setup time, even in the situation where we're running the 6809 at quad speed at approximately 4 megahertz, where each quarter cycle, is giving us about 60 nanoseconds. Because in any case, the setup time we need for read data is for 80 nanoseconds for the 6809E, and you're not going to clock a 6809E so fast that you're not going to give it 80 nanoseconds. 60 nanoseconds for the 6809, for the 68A09, and 40 nanoseconds for the 68B09. At least I would think that this would be perfectly safe, that we can use the falling edge of Q. So, do we have Q attached? And we do not. We have E. Again, the only clocks we need to pay attention to right now are Q. Everything else that we need to rise up on is on, as far as the addresses, we have another signal that will give us those addresses are valid. And if we do this on the falling edge of Q, we know that we'll be providing valid data. There is the possibility that we might need to provide valid data on the rising edge of E. If that's the case, fine, we can do that. But that is not what I'm going to plan on right now, at least not with the standard speeds that are currently available, where you overclock the CPU to 2 megahertz. At any rate, this brings us back to the PIO code and also to how things are wired up. This is why having, only needing up through A12 is helpful, because now I can add in both the Q and the SCS lines and have room to spare. So let's see if we can't figure out how to get this put together in code. Not knowing exactly how this bit here works, I'm going to play with that a little bit as an incantation and worry about how to make that work later. Instead, I will add in another file to put in, and I'm going to do that on another screen. Get CoCo interface.pio. I will open that up and double click that, move that over here so I can split it and see what I'm working on. And let's see what we can do with this. All right, okay, this is the GPIO. Got it, never mind. I'm doing this stupid. We'll try this again. Clock pin was at GPIO 25. Read write is at GPIO 24. GPIO 26 has CTS, and SCS, let's see, Q, I need it to be at GPIO 23 because that's where CTS is already defined at 26, and SCS I need to be at 22, GPIO 22. There we are. That's better. And I still have A13 available, so I can do a 14-bit ROM width. In a cartridge, if we're doing cartridge emulation, we only need reading. We only need writing data from the Pico. In the case of an SCS, we might need to read. So at this point, we want to wait until Q goes low. We know we've got valid data on the bus once Q goes low. And we're going to use a flag to tell the CoCo to do something. I'm not sure if this will work. I'm going to try. I'm going to do this to be on the safe side, because I know that once E goes high, I'm safe for valid data. All right, now let me double check this, because that was the other reason we needed E, is when E goes low, that indicates the end of the data read section, so we do need E definitely for that. All right. If this is 10 nanoseconds, though, let's stop and look at this for a second. I don't want that to be a full 10 nanoseconds, because here's again, there's our timing. Where's our timing? This value here, this data hold time, both number 18 and number 21, that read data hold time and write data hold time, those are, let's see, 10 nanoseconds for the read data hold time and 30 nanoseconds for the write data hold time. That's a pretty significant amount of time when you're looking at a 60 nanosecond window from the bottom of, or actually 120 nanosecond window. So here we're assuming, because this is going to be available almost immediately. We've got a little bit of time for things to work after we tell the proc we've got a bus assert to handle. We wait for the rising edge of E to pull the byte. That still gives us plenty of time to set that. This will set that. Let's say that's going to take 10 nanoseconds, 20, 30, 40. So that will be 40 nanoseconds that we're waiting from the rising edge of E. And that brings us right up to, where's my timing diagram? The rising edge of E. And that brings it 10, 30, 40. That brings us right up to that quarter length. Well, okay, we've got enough time. So that can be a 10 nanosecond. That can actually be 10 nanoseconds. Actually, no, I can do 5 nanoseconds, because this waits for 0, GPIO E. I think 5 nanoseconds is correct. I'm not sure. I'll have to look at the other code to see what the timing was set to. And I have to look at the datasheet. Actually, let me look at the datasheet now to see what happens with this. We wait 0 GPIO E. There's at least one cycle there. It triggers when it triggers on the falling edge. And the question is, does the delay happen after the trigger occurs? Delay cycles begin after the instruction completes. They do not begin counting until after the wait condition is met. Okay, so the wait condition, once it's met, it runs, and then it does the delay, so that's going to be a 10 nanosecond delay. So I will want to load this entire block of code into the PIO as one go, with the distinction being that I want PIO2 or no, I want the second PIO instance to start here. One of them starts here, one of them starts here. And we've got that. That's only going to serve that interrupt. This should work. I'm not entirely sure how well it'll work or if it'll work, but it should work. The next trick is, what does it look like to set up our CSDK? This should be contiguous in memory, and right down there at the bottom, I should be able to, oh shoot, oh dear. So the problem I face here is that I need to jump back somewhere, and I'm not sure where I need to jump back to. Doesn't want to like that. I don't understand why it doesn't like that, but that's okay, because I'm pretty sure that's correct according to PIO code. The other trick I can do is do an X minus minus. So that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 instructions, which is fine because I've got 32 to play with. And the next thing I need to do is figure out how in the heck to write this CSDK thing. On further reflection, this is going to cause more difficulty than it solves, which is unfortunate because I'm going to run right up against how many lines I can have. Seven, 28, 29, 30. It's filling up that memory pretty darn quick. But at least this way, I'm not having to jump all over heck and gone to get things going the way they need to go. So this is what I'm not entirely sure what's going on, and I have no idea where I'll find documentation for this. I've seen a couple of things that tell me some stuff, but I really don't understand what's going on. It's a little bit of an incantation, as with several things, it seems, with the Pico SDK. So far, this all makes sense. We pick our PIO, we pick our state machine, we tell it where to go, we tell it what we're looking for in and out, and now we do our starting things. So the first thing is to define a config object. I really don't know what a config object is. What is a config object? Ah, I know what these are. I know exactly what those are. That's the pin we're looking at for exec control. This pin we're looking for shift control. All right, got it. So now that makes a lot more sense. This is just an information block, and all we're doing here is we're getting our config information block that we'll pass around. And all we're doing here is grabbing that config information block pre-populated with the program name. which is, yeah, that's 200 000 000 000. Yep, that's 250 megahertz, all right, which means that I will not need to do any type of clock dividing on this. All right, that makes a lot more sense now. No clock division on the PIO. It's saying, 250 megahertz will give me what I need there. If it's 133 megahertz and I delay 3, let me do that calculation. Do I have that up? And that is 7.5 nanoseconds, which gives me a 22 nanosecond hold time, which is plenty. All right, cool. Now this whole incantation begins to make a lot more sense. This is being put together and put directly into a header file that can be used to activate the thing. So this is writing the function that sets up and activates the PIO. Now it begins to make much more sense. All right. I think I might need cmakelist.txt. I'm not really sure. Maybe that just did it. All right, let's try it. Oh, okay, nice. So it does need make. All right. Before it'll figure something out. Let me see what I've messed up. All right, awesome. So this is how it works. So 29, expecting comma, relinquish the output out, pindeers. Where did it go? That is online. Oh, wait, whoa. Hang on. That's my problem. All right, so that was the line number because it was line 29. All right, got it. It always has to have that specified. Good. That should work. Let's try that again. It built. Lovely. So let's look at this and see what we have. All right. So it looks like this is ready to move on to the next phase of testing, which is figuring out how to get it to run in the environment of the Pico. And I'm happy. I'm happy that I got PIO code to assemble first and foremost, and that I managed to grok what was going on with the PIO code. So PIOs make a lot more sense now. It's difficult to explain, but at least I see what's happening as far as the state machine to a certain extent. I know we haven't seen anything working yet, but for me, that's okay for right now. I'm more concerned about making sure that I learn what's going on with the PIO, and it looks like I more or less understand what the PIO is doing and how the PIO works, and I can see where there's some very strong potency in using the PIO for certain tasks. All right, we'll test that once I figure out how to get it tested, which is going to be in the next installment. In the meantime, I'm just happy that I have compiling code, and I'm one step closer to have a working full bus implementation of the FujiNet device. So we'll see how this works out on our next installment of FujiNet stuff, right here on the break key. Like, share, and subscribe.